Hello, this is Sandeepa, and along with my two mates Srikansh and Shubham, we are going to present this paper authored by Jiling Yang and others from Carnegie Mellon University and Google AI Brain Dream. So, XLNet is the first model to beat BERT, which was the previous state of the art in a lot of NLP tasks, and achieved a state of the art results on 18 of the 20 tasks, including question answering, natural language inference, sentiment analysis, and document ranking. Unsupervised representation learning has been highly successful in the domain of natural language processing. Among them, autoregressive language modeling and autoencoding have been the two most successful pre-training objective. Uh, Autoregressive language modeling seeks to estimate the probability distribution of a text corpus given a text sequence X. Here X is a sentence, and this can be naturally factorized into a product over the words where the probability of each word is only dependent on the words before it or after it. Since this language model is only trained to encode a unidirectional context, either forward or backward, it is not effective at modeling deep bidirectional context. In comparison, autoencoding based pre-training does not perform explicit density estimation, but instead aims to reconstruct the original data from the corrupted input. A notable example is BERT, which has been the state-of-the-art pre-training approach. Given the input token sequence, a certain portion of tokens are replaced by a special symbol mask, and the model is trained to recover the original tokens from the corrupted version. However, the artificial symbols like masks used by BERT during pre-training are absent from the real data during fine-tuning, resulting in a pre-trained fine-tune discrepancy. So let us consider the example New York is a city. We were asked to predict these two words, New and York, and the context here is a city. Now, if you compare BERT to what XLNet does, what BERT does is that it simply masks these two words and say, here, please fill in these two words. This translates to the objective being separated into two portions such that the prediction of York here is completely independent of the prediction of New. So, if you know of any other city that is made up of two words, for example, Los Angeles, then BERT might end up with Los York as a city, and that would be perfectly fine for BERT. So these are the kind of mistakes that BERT can get into by not being autoregressive, whereas XLNet would specify an order. Let's say, okay, first I'll predict the word new as the first word, and when I'll predict the word York, then I'll take into account that I previously have predicted the word new. So that's the main advantage that autoregressive training has over autoencoding. So faced with the pros and cons of existing language pre-training objectives, the authors propose XLNet, where instead of using a fixed forward or backward factorization order as in conventional autoregressive models, XLNet maximizes the expected log likelihood of a sequence with respect to all possible permutations of the factorization order, thanks to the permutation operation, which will be explained in detail by my teammate. And in addition to a novel pre-training objective, XLNet improves architectural design by integrating segment recurrence mechanism and relative encoding scheme of transformer XL into pre-training, which empirically improves the performance, especially for tasks involving in a longer text sequence, which will be discussed in detail by my teammates. So over to you, Rikansh.
Okay, so thank you, Sandeepa. Yeah, so thank you, Sandeepa. I'll continue with the example that Sandeepa had discussed. So I'll discuss with the sentence New York is a city. So first of all, why we need permutation and factorization. So I'll explain with the help of this example. So New York is a city. So if I have to predict is and a words, both words I have to predict. So if I want to predict is, then we have to take the account of New and York. So on if I have to predict the word A, then we have New and York. So what I will take in the first order, if I have to predict is and a both, so I'll predict is or first I will predict a. So these are the questions. So that's why we needed permutations and factorization. And in the second example, New York is a city. So if I have to predict is and a, so is on the first location and a is on the second location. So for for is I have nothing to I have nothing to with to help the predict is. And for a I have is, but is also is not predictable, because is I have to predict is also. So these are the kind of the problems, that is why we needed permutation and factorization. So yeah, what was the objective of permutation language model? So this was the objective which I had discussed previous in the slide. So I will describe briefly with the help of these diagrams. So in this diagram, in the first diagram, if I have to predict x3 and the factorization order is 3, then 2 and 4 and 1. So if I have to predict x3, then before 3 there is no number. So I do not have any word to help to predict this x3. So I'll take help of the memory, which is on the basic layer, that is memory of 0. So I'll take help with this memory, and this is gradient free, and it has some primary information. So with the help of memory, I'll pass the information to first hidden layer, and then second hidden layer. In second hidden layer, I'll use the information of memory in the previous layer, and with the help of this, I'll predict x3. So these are the permutations. That is why we use permutation models. So like here there are four words. So permutation is 24. So we needed 24 permutations, and now I'll have to combine all these permutation in one architecture. So yeah, so these are some properties of permutation language model. It gives a sequence X of length T, and this is uniformly sample and factorization order Z from all possible permutations, and it maximizes the permutated log likelihood. So the objective in the mathematical notation is described by this. So maximum of expectation of Z, that is sampled from ZT, that is the combination of all permutations, and the summation T equals to 1 to T log P theta, that is probability, log probability xzt, given by xz less than t. So xz less than t is x less than t is the word which you have to predict. So before all the words we will take. So this is the formula. Now I'll discuss the architecture, that is two stream attention for target aware representation. So in this architecture, in order to achieve achieve all the permutations, we have drawn the architecture. So we'll draw a single architecture to find the all probabilities. So they do this by masked two stream attention. So there are two hidden representation instead of one hidden representation. So H is initialized with the embedding of the tokens, and G gets initialized randomly, then they get transformed. The point is the H of next layer is always to look at the same and the previous layer, and G has to look only to H before the current position, and H is allowed to look at the same and the current position. So, and these information are passed in the next layer, and we predict the words which are not visible, which are masked basically. So this is how architecture works. Now implementation detail. There are two implementation details, that is content stream visualization and key value query stream. So content stream is XLNet introduces content stream and query stream. Content stream is actually similar to BERT, however they mask the order in order to predict the word. And now we'll come to query stream visualization. That is, in order to prevent sort of peaking into the future, we also create what's called query stream, which also builds in parallel to content stream. So now we'll talk about query stream briefly. So we have the same factorization order which we talked in content stream. So in order to overcome the peaking, they actually used a positional encoding which is represented as W. So we look the word position which has access, and instead of the content, we use positional encoding that is being built, and that is at word 4. So the idea here is that we want to use location of the word in order to predict the word to build the language model. So this is the idea the by which we needed query stream visualization. So yeah, these are the formulas which I discussed in the last slide. So gz is GZ is generated by the last layer and the current position, and with the current position, and key value is generated by the last layer and before the word which you have to predict. So uh, the previous words by with the help of previous words. So yeah, query stream encodes target position information, and content stream encodes both context and the target word. So now rest of the paper is incorporated ideas from Transformer Excel and some results and some discussion. So my friend Shubham will explain this part. So thank you.
Thanks, Rekhansh. So, authors have incorporated two main ideas from the Transformer Excel. They are first one is relative positional encoding scheme, which is applied based on the original sequence. The formulation uses fixed embeddings with learnable transformations instead of learnable embeddings, and thus is more generalizable to longer sequences at test time. The second one is the segment recurrence mechanism, in which the memory concept is explained. So the memory concept is incorporated from Transformer Excel, which uses the segment recurrence mechanism. In this, they want to have a recurrence between different segments of the text. In order to add that recurrence into the model, they make a sequence of two different segments. First, they train the network on the first segment, and they go all over the layers and do all the training on that, and use all the hidden state h and g functions over there as a memory in order to use that input to the next segment of the training process. So here we consider z and z tilde as a permutation, and x and x tilde as the segment. So the attention update with the memory is given by this formula. So the discussion point is XLNet is capable of capturing the dependencies between the tokens, whereas BERT ignores such a dependency. The example given by authors is the New York is a city, which is already explained by my teammates. So results, as a BERT was the successful model before the before XLNet. So authors have compared XLNet with the BERT. So in BERT, they have taken three BERT versions: original BERT, BERT with whole word masking, and BERT without next sentence prediction. So here we can see the results are improved with the XLNet. After scaling up, that is by adding the 24 layers. So here also you can see on different models, XLNet performs better. On a SCOR dataset, that is a reading comprehension dataset, the results are also good for the XLNet. So in ablation study, these are the three main aspects we hope to study. So the effectiveness of permutation language modeling objective alone, the importance of using Transformer Excel, the necessity of some implementation details, span-based prediction, the bidirectional input memory, and next sentence prediction. These are the main data set used in the ablation study. Race score 2.0, EMNLI, necessity 2.0. Then in ablation study, authors have taken the 8 cases. Uh, uh, First one is the BERT basic model. Then another second one is denoising auto encoding plus transfer on Excel. Then XLNet with constant k equal to 7, where this k is a hyperparameter to control optimization difficulties. So in first four, if you compare, you can see XLNet performs better over BERT and D plus transform Excel. So next authors have tried removing memory. So also here we can see the accuracies on those four data sets is decreased. Also, authors also tried removing span-based prediction and bidirectional data. In both of these cases, also uh, accuracy is decreasing. And also, when they added next sentence prediction, almost accuracy is decreasing in all the data sets. And these all results reported are the median of high runs. So the conclusion and key takeaways. The permutation modeling in XLNet performs more effectively than that of BERT. So XLNet combines the advantages of autoregressive and autoencoding methods. So XLNet integrates the transformer XL architecture. XLNet introduced the two-stream attention mechanism, that is query and content. XLNet covers more dependencies than BERT. So these are the references we have used.